So we have few TAs also for the course. So Paritosh is there, and who else has joined from the TA side? Paritosh, are you there?
Yes, sir. Good morning. I'm there.
Yeah, good morning. So there are two more people,
Okay.
two more TAs. So you may contact them later if they don't join here.
Okay. Okay. Okay.
Okay. So basically, TAs would be helpful to all of you in having your assignments submitted and other things if there are some problems during the course and session. So any difficulty you can share with them. So their contact number, email ID, they can share in the group, in the MS Teams group. So you may contact them anytime. And in case of any difficulty, you may contact me also anytime. Okay, so we'll start the class. Let other people join whenever they are joining. Okay, so basically, this is the Advanced Electric Drives course, and myself, Dr. Avnish Tripathi, I will be the sole instructor of this course. So some prerequisites are there for this course, which are like basic power electronics you should know and the basic electric drives. So this is particularly for the people who are like in MTech first year. So they must have taken this course, and who are in PhD first year, that is all right. You need not worry. So the basic power electronics course includes like the understanding of semiconductor devices, some basic understanding of DC-DC converters, DC to AC converters, AC to DC converters, and some understanding of basic pulse width modulation techniques. So I will also be covering these things as part of review and then some of the things in a more elaborate manner. So as and when required in the course. From the electric drives point of view, we need to have some understanding about the DC motor drives, not necessarily the complete closed loop control, but some understanding of that, and the open loop AC motor drives. So we all must have studied that during our masters at some point of time. I'll be covering some things as a review of this course. Now this is the course content which I'll be largely covering in the next 41 classes. So this is something like review of basic motor drives which you have studied in the previous courses, and we will have a more thorough understanding about the open loop and closed loop control of induction motor drives. We will review some of the PWM techniques which are quite popular like sine triangle, space vector and all these things. Then we will have some discussion on PMSM motor drives, the BLDC motor drives, SRM drives, and on the later part of the course, we will go towards some of the advanced things in motor drives. Let us say the CSI fed motor drives, which are being utilized in the industry, some advanced control techniques which are available in the industry like DTC, etc. And one case study we will do. So here we will take a particular application which we will discuss. So this could be traction or this could be anything other similar to this. So case study would include basically how do we design the converter completely. Let's say we have the understanding about the load and about the system, but how to go on to design the load, how to start the system, how to stop the system, what to do if there is some supply fluctuation and all these things. So this will be the part of the case study towards the end. So during the course, some books we will be referring. So here are some of the suggested books. These are also given on the website. So one book which I would say, the Control of Electric Drives by Werner Leonhard. So this is something which is the most fundamental book you can say on electric drives. So this is a quite handy book we all should have. So at least through the library or somewhere you can get the access of the book. Other books also would be useful in one or other topics. So now this is how the credit is distributed for the different parts. So this course includes lecture, which is like 3 hours in a week, and there is also a practical uh, time allotted for this course, which is basically simulation. So the complete clarity will come in a day or two, but as of now, the time allotted is 2 hours in a week. So that is on Tuesday afternoon. So otherwise, the lectures are on Tuesday, Wednesday, and Friday. And Saturdays, whichever working day falls, accordingly, we will take that. Now the marks distribution. So for all the class assignments and other, let's say we have some quiz sessions and all, there will be weightage of 15 marks. And then we have some weightage for the practical assignments and all practical reports, which will be preparing on basis of the simulations. So that has a weightage of 25 marks. And then there will be a midterm examination, which will carry a weightage of 20 marks, and end-term examination, which will have 40 marks. So there will be only theory examination in this course and no practical examination. So for practicals, we will have only simulation report submitted by you. So then this throughout the semester, we may have 10 or more than 10 assignments where I will consider the best 10 for the grading. And for simulation exercises, we will have 5 simulations throughout the semester, which will be distributed for different kind of drives and different kind of systems, which we will discuss in our class. Now, with this background, let us discuss quickly what are some of the applications of motor drives. Let us say when we talk about any system, we first need to know that where it is being applicable or where it is available or existing in industry or any other place. So if you talk about motor drives, you can have the application of motor drive in every aspect of our life. Let us say if we start from propulsion to pumps, fans, compressors, any plant automation or spindles or aerospace application or robotics application for cement industry, steel industry, paper and pulp industry, textile industry, automotive application, then underwater or mining applications. Then we have conveyors, elevators, accelerators, lifts, everything. The other appliances or power tools which we see. So lot of companies, let's say Robert Bosch or something, they are making lot of tools and all are being basically run on some type of motor drive. Then we have huge antennas being controlled through some motor drive, machine tools. So these are like larger aspect of our industry is occupied by the motor drives. So which means this is very, very essential that we understand the basics before applying this into any design or any other kind of thing. So when we say motor drives, what we basically understand with that? So certainly we have an electric motor which is attached to some mechanical load. So electric motors are basically converting the electrical energy to mechanical energy, and this mechanical energy is getting fed to the load. So in all the applications which are stated over here, we have by and large this kind of system where we have electric motor running some kind of load. Now these loads may have different dynamics, different nature, different characteristic. So these things we will understand, like if we have a particular dynamics or characteristic requirement, which electric motor or which kind of control is suitable for that application. Now with this background, let us understand some basics about the dynamics of the mechanical system, because this is what we are going to deal with in larger part of our course. So first we should understand when we talk about load, what is the meaning of load? What is the dynamics associated with that? So as I said, there is an electrical motor which is connected to load. So which means, and primarily because we are talking about all the rotational kind of systems, so certainly there is some moment of inertia attached with the system. There is some angular speed attached with the system. So now if we, let us say, write a generic equation for this system, we have the electrical torque generated, which will be basically countering the load torque requirement, and plus it will be contributing to the change in angular momentum. So this is the generic equation, we can say, where we have a system in which the J can also be variable. Now if we expand this system, so two terms can come out from here. And regarding the omega, so let us say this is our cylindrical structure where we have a reference axis and our cylinder is rotating with respect to that. So any change in that angle, that is basically associated with omega. So omega is nothing but the rate of change of the angle from the reference axis. Now here, in this course, largely we will be dealing with this part, and systems where our J is variable. This could be a very minor part of our course. So largely we will have systems where J is fixed. So our system will basically be defined by this dynamic equation. There could be some frictional components also, let us say plus B omega and so on. So whenever this is present, we will include that also. So now, when we talk about steady state operation, that time our omega is constant, which means any change is zero. So our electrical torque is basically countering our mechanical load, and this is what our system is doing under the steady state operation. Now from the power point of view, if we try to understand this and we multiply this whole equation by omega on both the sides, we have this basically represents how much electrical power we are giving into our system. This section represents what is the load, what is the power taken by the load which is attached to our machine, and this is basically rate of change of our kinetic energy. Again, under steady state, there will not be any change in the kinetic energy, and our entire electrical power would be fed to the load. So this is under steady state. Now, if we talk about the energy consumed by the system or how the energy is getting distributed in the system, so if we integrate this power equation over a time t, so we would find the electrical energy fed into the system has basically gone into two parts. One thing, the energy which is consumed by the load, and another part which has gone into raising the kinetic energy of the system. So this equation, which we call as energy equation, is always true. Whether it is under the steady state condition or under the transient condition, this equation always holds true. So some of the quantities, let us say, if we say energy or our angular speed, our the angle epsilon, these are like continuous quantities. There cannot be any abrupt change in these quantities. So these are also called state variables. When we talk from the control point of view, these are the state variables which we try to control. There could be other quantities like power, torque, which may be discontinuous. By discontinuous, I mean that over a period of time, if you are seeing, there could be some positive value of this quantity, and then next instant, the demand could go on the negative axis. So there could be abrupt change in the torque and power values. So these are discontinuous. Now, when we have understood the basic equation, another important aspect about the mechanical system to understand would be the nature of the load torque. Let us say when we are writing this equation, and we are designing our system, we must know what is tau L, what we are dealing with. So in general, the torque could be function of lot of quantities. This load could be function of omega, time, etc. Lot of quantities it could be function of. So here we will deal with quantities which are independent of time. So largely it will be dependent on omega. So let us say a generic term, if you try to write for the load torque, it could be of this form. This could be most generic form in which a load torque can be expressed. Now, some of the torques could be like very specific type. Let us say, first, if we talk about a load, something like crane or something, some application. So here the load torque requirement is like a constant value. It does not vary with omega. So we have to maintain a constant torque irrespective of any rotational speed what is there. So the tau omega characteristic could look like this. The second type could be where we have dependency on a constant term, which could be a frictional, and then it could be associated with the omega in a linear form. So the applications like excavators and these kind of things, they include such load characteristic. So here either we may have tau omega characteristic like this, where there is some k naught value, or we may have k naught value close to 0, insignificant value, so it may start from 0. The third type could be where we have a quadratic relation with our angular speed. So all the fans, blowers, these kind of applications, they basically employ this kind of load characteristic. So the tau omega curve may look like this, where we have a finite k naught, or it may start from 0, where k naught is insignificant. Now, so on, we can keep going like this for different applications, and we can always plot the tau omega characteristics, and this tells like what torque we need to generate at different omega. So whether our system is capable of generating that or not. Now, there could be some special requirements in terms of load. Let us say if we talk about a traction load, here the torque is defined in a discrete manner. Let us say a constant for some range of omega, then inversely proportional to omega for another section of angular speed, and then the requirement may be insignificant for omega greater than the omega 2. So this is how a typical traction load requirement looks like. So it will be like this and then suddenly falling to zero, which means when we are going to very high speed, the load torque requirement is like almost not there. So then this defines that when we are having any motor being applied in a traction application, what we need to generate at different omega. So having said that, now the next important thing to understand from mechanical point of view is when we are applying or dealing with a system and some load torque is there and we are able to balance that. But whether that operation is stable or unstable, which means let us say you have a load torque requirement and your motor is having this kind of characteristic, load torque characteristic. So at the point of intersection, we are having our nominal operation, let's say at omega naught. Now, if you disturb the system by a small quantity, let us say delta omega, whether the system is going to restore to that point omega naught or it is going to run away from omega naught. These two questions, so whether delta omega will go to zero as time approaches infinity or delta omega will run to infinity as time runs to infinity. So this defines whether our system where we are having this motor and load getting connected, whether it is stable or unstable. So again, coming back to our equation what we have seen earlier. So because this is a dynamic situation, so we will consider this j d omega by dt as well. Now let us say you introduce a perturbation of delta omega in the omega angular speed. So your new speed becomes like this. Now corresponding to change in omega, you can see that if we perturb the omega a little bit, there is change in tau L and tau E as well. So corresponding to this perturbation, the tau E may become something like this, where tau E naught is the value at the nominal operating point, and the tau L may become something like this. So tau L naught is the value of load torque, the nominal value of load torque at the omega naught. Now, if you put that in equation, very easily we can see that the other quantities will balance out and what will be remaining would be your now this first order homogeneous equation, this defines whether this quantity delta naught is going to go to zero or going to go to infinity as the time approaches infinity. So if we try to solve this, now first we will have a reasonable mathematical expression for these terms. So let us say we write like this. So here it could be omega, dou omega e by dou tau e by dou omega into del omega minus so this is a reasonable mathematical expression, what we can say, where we have clearly defined our input or our variable and the other quantities. So if you have difficulty in taking delta omega as one quantity, you may consider delta omega as some x or alpha. So that will simplify the terms for you. So we are basically looking for the delta omega, that what value it will attain with time. So this is something similar to a constant value, because whenever we perturb omega, we know that how much this is going to change. Basically, this is the slope of tau e with respect to omega, and this is slope of tau l with respect to omega. So this is more or less a constant times of delta omega. Now, this equation, if you solve, so what we are going to get? Delta omega will turn out to be in this form, where delta omega naught is the original perturbation. Now we can see clearly the exponential term, this will reach to 0, which means delta omega tending to 0, only if the k is negative. Because j is a fixed quantity, we cannot do anything about that. So k is the quantity where we are putting up things. And delta omega will reach infinity when k is greater than 0. Which means what? These are the stable and unstable conditions for the load and the electromagnetic torque. Now, the third scenario is also there. Let us say k is equal to 0. So, which is a system when delta omega will remain at delta omega naught. That is, the system is indifferent. There is no change in system in any scenario if you perturb by a delta naught value. Now, what is the meaning of this k greater than 0 and k less than 0? So when we say like k less than 0, basically what we are saying that our slope of the the electromagnetic torque should basically be lesser than the load torque. This is the condition for a stable operation. And when we say k is greater than 0, which means the slope of the electromagnetic torque is basically greater than the slope of the load with respect to omega. So if we see graphically, if we visualize that how it looks like our scenario under the stable and unstable conditions. So if this is the case where your tau L and tau E are like this. So obviously the tau L slope is positive and tau E slope is negative. So here your del tau L by dou omega is basically greater than the electromagnetic slope. So if you have any perturbation given in this system, wherever it goes, basically it will retrieve back to the original value, which means delta omega will become 0 with time. So this is a converging system. The second scenario could be, which is like the unstable system scenario, where we have the exact opposite of this. Let us say this is your electromagnetic torque and this is your load torque. So clearly here the dou tau E, dou omega is greater than the load torque slope. Now any perturbation given to this system will basically take the point away. So either the system will collapse with speed going lower or it will collapse with speed going higher. So physically also we can interpret, let us say any system is there. You are feeding the electromagnetic torque to any system which has requirement tau L and you are having the input as tau E. Now this is running at some omega. Let us say you increase omega and with the increase in omega, you have the input torque getting reduced and your load torque is getting increased, which means what? There is a tendency of deacceleration or retardation in the system because your tau L is becoming more and tau is reducing. So with increase in omega, there is deacceleration. So which means your omega is going to come down. So you have increased omega and it is coming down on its own, which is the indication of a stable system. On the contrary, if let us say you change the omega, let us say you increase the omega and your tau E increases and tau L reduces, which means any further increase in omega is actually giving you acceleration, which means the omega L will keep on increasing and your system will see an unstable operation. It will keep on going till it collapses. So physically we can interpret in that manner. So this is the basic understanding of any stable or unstable operation. So this is the famous thing what we know about the induction motor, that we have a unstable zone of operation and we have a stable zone of operation. So this is how this is related to this. Any constant load torque or any fan load or any load torque you can take and you can compare how these quantities are coming up for the induction motor and that load. So you will clearly see that in this system, the system is coming to, or in this zone, the system is coming to be stable. Whereas in this zone, it is unstable. It may either run away from that speed or it may collapse to zero. So this is the basic understanding what we have got about our load, whether it is stable or unstable. Now, of course, when we are having motor drives, there could be different quadrants of operation. By different quadrant, I mean your omega could be positive or negative and your load torque also could be positive or negative. So we have the electrical motor feeding the load. So where omega is the rotational speed, it can be either positive or negative, and also our torque. Now based on this, we define that our motor or our system is operating in which zone. Let us say I divide this in 4 quadrants. So we have torque and we have omega. So in the first quadrant, we have both the quantities positive, which means this kind of operation for any motor where we have input torque also positive and your omega is also positive, this kind of thing is called motoring mode, which means the motor is operating in motoring mode, means it is taking power from the electrical side and giving power to the mechanical side. Now, the second quadrant where let's say our omega goes negative, but our torque is still positive. So if our omega is going negative, we are basically running on the opposite direction or on the negative side, and we are applying a positive load, a positive torque, which means we are trying to reduce our negative speed or basically bringing our magnitude of the speed to closer to zero. So that is why this is called braking zone. But because this is going in the reverse omega side, so this is called reverse braking. Again, the third quadrant where both the quantities are negative. Our torque is also negative and omega is also negative. So which means what? We have certain value of omega in negative direction and we are further increasing that. So this is again the motoring mode. But because our omega is negative, so we can call it reverse motoring mode. So here to classify, we can call it forward motoring mode to distinguish from the quadrant 3 operation. Now in the fourth quadrant, we have omega positive, but we have torque negative, which means certainly we are trying to bring down the speed from a value closer to zero. So that's why we are braking. And because it is in the positive direction of speed, so this is called forward braking. So similarly, you can identify how the power is flowing. Let us say if I assume this direction as positive, which means from electrical side to mechanical side, because essentially it is a motor drive. So this direction as positive, and the other direction where we are having the reverse flow from mechanical to electrical side. So this we call as negative direction of power flow. So then we will clearly see that we have positive power flow in the first quadrant and in the third quadrant, and we have negative power flow in the second and fourth quadrants. Correct? So this is how we are going. Now, when we are telling the quadrants for operation of motor and the load, we do have some restrictions over how much speed and how much torque we can have for any system. So these are called basically the ratings of the motor or ratings of the system. So there are basically two classifications for the ratings. One is what is called continuous operating or continuous rating, and another is called shortened. So continuous rating refers to when we are running the system for few hours, let us say even for over a day or something. Still, the system should be reliable for this duration of operation, which means the temperature should not go very high, the performance should not degrade. Then we say that this is a continuous rating. The short-term rating is something which is like meant for a few minutes of operation. So here, let's say the torque or some quantity we are taking to extreme value for some time, and then we are bringing back within the continuous rating, then that is called the short-term rating. So we are not violating the thermal limits, but we are still doing or going little bit higher from the regular duty, then that is called the short-term rating. Now on the torque omega axis, if we see, because omega is largely dictated by the limits on omega are dictated by the mechanical bearings. So we do have a rigid limit over here, which is whether you call it short term or continuous, it is same. So here we do not have any short term limit. Whereas on the torque side, we can have a short term rating and we can have a long term rating, or sorry, the one thing is the continuous rating and another is the short-term rating. So I am drawing the blue, which is the continuous rating, and red, which is the short-term rating. So that lies little higher in magnitude. Now, it is not like when we are drawing the limits on these parts, you can have any torque for the entire speed range. No, we cannot have, because there is another quantity on which we are putting restrictions on, the amount of power drawn. So we can have constant power operation for some range of omega, but we cannot have the same power being fed for the complete range. So somewhere we fall into the constant torque, or sorry, here the opposite. We cannot have constant torque for the entire range. We must have some restrictions beyond a certain speed, because we will be violating the power limits. So when we cross that this boundary where the power limits are coming up, then we go into something called as constant power operation. So let us say for this range, we are allowed to have our short-term torque at the rated value for this range of omega. Now beyond this, when we are trying to go, if you try to plot the power would be increasing, and then it will reach the limit. So beyond that, we need to have a flat, okay, I'll draw power in, let us say, green. So for clarity, so we have power reaching this limit and then it has to become constant. So which is where our torque will also come down. And it can have something like this. So similarly, for all the 4 quadrants, we will have this kind of plot. So this is happening. The power is having this. So in the third quadrant also it is positive. On the second and other quadrants it is negative. So I will just draw the magnitude. So everywhere we are having this kind of plot for power. Now what about the short-term duty? The short-term duty basically means the torque we can take little higher for a very short amount of time or short duration. So here we have the torques going up to some higher value. And again, because there is a short-term power limit also, so it will not be valid for the entire speed zone, and it will also have something like this. So for this also, if we draw the power, it will be little higher, of course, because this is short-term duty and then going constant. So this is how our limits on the torque, omega and power, if we plot with respect to omega, would look like. Now this we keep in mind when we are running any machine or any system. We must know what are the limits on any quantity. We cannot keep on increasing the any quantity beyond its limits. So if thermally the machine or any system is violated, there could be breakdown in the system, and that could be disastrous. So that's why this is very, very important. Now moving to the last section of today's lecture. So we have the electric drive. Then what do we mean by electric drive? When we say that we are working on electric drive, then what are the different components or different sections on which actually we are working? So when we say electric drive, certainly we have a motor. There is no doubt about it. And we have a load attached with that. So of course, when we have electric motor, then definitely we will have some power source feeding that motor, electrical power source. Now in most of the cases, what we will go through during this entire course, we will not be feeding power directly to the machine, which means we will not be having direct online start or any such kind of thing for our system. So we have to have an interface which is called power converter or power amplifier or power actuator, whatever name you want to call it. So this will be taking supply or taking power from the electrical source, and it will be feeding the electrical machine. And then the electrical machine would run the load. Now, in this exercise, we must have some say over what power this power converter will generate, which means what voltage and what current it will be generating. Now that, if you see, all these systems which are drawn over here, these are all non-intelligent. They don't have any intelligence. The power source doesn't know how much power it has to feed to any system. If you short it, it will be like disastrous for this. Same for the power converter also, same for the electrical machine, and same for the load. So we must have some intelligent system interfaced with our drive. So that is what is called the controller. So this will basically command the power converter about what voltage reference or what current reference it has to generate, or what current it has to generate or voltage it has to generate, basically dictating the power operation for the complete system. Now the controller will decide these things on basis of certain inputs. Let us say the input given in terms of speed reference or the torque reference. Now, it may or may not have any other feedback system. So again, when we talk about this, we classify this into two parts. One thing where we do not have any feedback from any part of the system to the controller. These are called open loop systems. And the other one where we have some feedback to the controller, these are called closed loop systems. So major part of our course, we will be dealing with the closed loop systems, but some section we will also deal with the open loop system. Now, the open loop systems, of course, these are like the cost is lesser because the design is not so robust, and that's why we can have a lesser, let's say a weaker controller doing all this job, and hence the cost can be very low. Then the performance of the system will not be very great. It can be of the moderate level. Then where we can apply these kind of motor drives, the open loop motor drives, to all the applications which are non-critical. Let's say we have a fan at home. We need not put a closed loop control for that. It is just running on the power supply directly. So that is a non-critical application. It is not going to have any speed control or torque control demand. Whereas if you talk about air conditioning, definitely there is going to be a closed loop system, because there is some requirement at what temperature we are maintaining the air conditioning, at what temperature we are doing, what is the other performance criteria over there. So the moment we say that we have a feedback into the system, whether it is from the load or it is from the machine or it is from the converter, all these things then fall under the feedback control or closed loop control. So the load may give the omega feedback. So most of the time there is a filter when we are taking the omega feedback. There could be some torque sensors also attached to the load. So that feedback also we may have again with some filter. We may have the output generated from the power converter that is being fed as a feedback to the controller. So this could be your voltage, current, everything. We may have feedback from the power source side. What is the input voltage? What is the current flowing into the system? These feedback it can have. Now, based on these things, the controller will decide what should be the reference voltage and reference current generated from the power converter. Now, the beauty of closed loop control is in most of the systems, we try to make the steady state error close to zero, which means a very good performance. And this is coming on basis of the additional cost. There are more sensors, the controller is more robust, and it is like probably more capable controller, and lot of other things which are getting involved in this, the filters and all. And the applications where we put these kind of systems, those are all critical applications. Like I said, the air conditioning and let us say traction, and we can have some other electric vehicles which are run on the closed loop control. So these are the basics which I wanted to discuss about the motor drives in the first class. Now, moving further, we will have discussion, more detailed discussion on some specific kind of motor drives. Let us say the DC motor drive or the induction motor drive or any other type of drive. So where we'll be dealing with how to design the converter, how to design the controller, and what action we should take when we have any such load requirement, how the converter should be designed in the sense like what device, what other things we need to select. So these things we will discuss in the subsequent lectures, and today's lecture we end over here. So next we will be dealing with the other things which we have discussed. So thank you all, and then we will meet in the next class.
Thank you, sir.
Thank you, sir.
Thank you, sir. Thank you, sir.
So any doubts you have, you can either post it to TAs or you can post directly to me. We will discuss in the subsequent sessions.
Okay, sir.
Hello.
Yes, Paritosh.
Hello, sir. Good
So
afternoon.
this recording, if I stop, it will be saved, right?
Yes, sir.
Okay, so I am stopping this.